this with the rest of the class. It's just that they don't check what is happening on Moodle. So in fact, I wanted to check who is really aware of what is happening in MAT1141, but the majority are waiting to be told by their friend if there is something rather than going there to check for themselves. So let us just record this and we will share afterwards. But since you are here, it will be good. You may ask me questions where you don't understand. It's an advantage. Okay, but of course, you are not going to disturb me. Right. So this is what we have. And this is going to give us the limit when x is approaching 25. Then we ask ourselves, is 25 in the domain of this function that we have here? Of course, you will realize that it is not, because if you put 25 where there is x, it will be 25 minus 25, which is 0. You put 25 where there is x here under the square root sign, you will have square root of 25. So it is 1 over 5 minus 1 over 5, which is 0. So we have got 0 over 0. So to remedy that, what we are going to do, we will multiply by 1, or kind of rationalize this, divide by x minus 25. Let us multiply. Sometimes it is convenient to just check what we have here in the denominator. So we multiply by 5 the square root of x over 5 the square root of x, like that. So if we do that, this will be equal to the limit when x is approaching 25. Then we multiply every term here by 5 root 5. So 1 over root x multiplied by 5 root x is just a 5. Minus, then 1 over 5 multiplied by 5 root 5, it's root x. Like that. Divide this by 5 square root of x. Multiply this by x minus 25, like this. Okay, we can put a bracket here. So that we end up with the limit when x is approaching 25 of 5 minus the root of x divide by 5 square root of x into, again, if we look at what we have here, then we check whether 25 is in the domain of our function or not, we will realize that when we substitute 25 here, we'll have 25 minus 25, which is 0. Therefore, 25 is not in the domain of this function. So let us factorize x minus 25. So if we do the factorization, this is what we have. We have x, square root of x, minus 5 into square root of x plus 5 close brackets, like that. So now we can cancel out some of the terms. We can cancel out some of the terms. We can cancel this and that one. So note that here we have 5 minus square root of x, and underneath is square root of x minus 5, which tells us that we will have a negative in the numerator. So it will be -1 in the numerator. This is equal to the limit when x is approaching 25 of -1. Divide this by 5 square root of x into square root of x plus 5, like that. So now when we substitute, because 25 is now in the domain of this function, when we do the substitution, we have -1 over, it's 5 square root of 25 into square root of 25 plus 5, like this. And this is going to be -1 over square root of 25 is 5. 5 times 5 is 25, multiplied by square root of 25 is 5. 5 plus 5 is 10. Square root of 5 plus 5. 5 plus 5 is 10. So this is giving us -1 over 25 times 10, which is 250, like that. All right. So let us go on. I just want to do also number 20, number 20. Let us see number 20. Number 20. Number 20 is about the limit when t, not x, when t is approaching 2 of what? Of 2 to the exponent of 2t plus 2t minus 20. Divide this by 2 to the exponent of t minus 4, like that. This is equal to the limit when t is approaching 2. Then again, we ask ourselves, is 2 in the domain of our function? And we realize that if we put 2 here as an exponent, it will be 2 to the power of 2, which is 4. 4 minus 4 is 0. So similarly, in the numerator, we've got 0. Therefore, we must factorize our numerator. So how do we factorize that? If you remember the laws of exponents, we will factorize it like this. It will be 2 to the exponent of t minus 4 into 2 to the exponent of t plus 5, like that. Divide everything by 2 to the exponent of t minus a 4, like that. So this is equal to the limit when t is approaching 2, and then we can see that this and that can cancel out. So we're left with 2 to the exponent of t plus 5, like this, which is equal to, now 2 is in the domain of this function. It will be 2, the exponent of 2 plus 5, which is 4 plus 5, which is 9. There we are. Right. I think we can also do 21. 21 is a bit interesting. They say we should evaluate the limit when x is approaching 1. And we have x to the exponent of 4 plus 3 x to the exponent of 3 minus 12. No, it's 13. 13x squared minus 27x plus 36. All this you divide by x squared plus 3x minus 4. So the first thing is to check whether 1 is in the domain of a function. And usually we look at our denominator and see what happens when we replace x by 1. So you will note that if we replace x by 1, we will have 1 plus 3, which is 4. 4 minus 4 is 0. Therefore, 1 is not in the domain of this function. Then we'll be required to factorize the numerator, which is not that easy as such. So one way of approaching this kind of problems is to use long division. Let me say here, we may use long division. So you will recall from grade 6 or so how long division works with the numbers. So in other words, we just want to write this, maybe in grade 11, you also did this. We divide, we have x squared plus 3x minus 4. We divide it into x to the power 4 plus 3x cubed minus 13x squared minus 27x plus 36, like that. So how do we do the division? We divide x to the power of 4 by x squared. So x squared into x to the power of 4, it goes x squared like that. And then we take this, we multiply everything here. X squared times x squared is x to the power of 4. X squared times 3x is plus 3x cubed. Then x squared times minus 4 is minus 4x squared, like that. And then we subtract x to the power of 4 minus x to the power of 4, 0. 3x cubed minus 3x cubed, 0. Minus 13x squared minus 4x squared will give us minus 9x squared, minus 9x squared. And then we bring down those 27x plus 36, like that. So then again, we divide x squared into minus 9x squared. We get minus 9. Then we multiply. Minus 9 times x squared is minus 9x squared. Minus 9 times minus 3x, it will be minus 27x minus 9 times minus 4, it will be plus 36, like that. Then minus 9x squared minus minus 9x squared is 0, 0, 0. So the remainder is 0. So it is telling us that our rational function here can be written in terms of the quotient plus the remainder over the divisor. So since the remainder is 0, 0 over x squared plus 3x minus 4 will just be 0. Therefore, this expression that we have here, our function can be written in a very simple way. Let me repeat it here for you. In other words, what we are talking about is the limit when x is approaching 1 of x, the exponent of 4, plus 3x cubed minus 13x squared minus 27x plus 36. Divide this by x squared plus 3x minus 4. This is now equal to a very simple thing. Limit x is approaching 1. We got here the quotient x squared minus 9. So in other words, we simplified this expression, this rational expression, into simply x squared minus 9, like that. So 1 is in the domain of this function. Therefore, we can evaluate our limit as 1 squared minus 9, which is minus 8. There we are. So maybe the last one here will be number 24. Number 24, which is the limit x is approaching pi over 4. And we have the sine of x minus the cosine of x, divide this by the tangent of x minus 1, like that. Before we do anything, we must ask ourselves whether x, pi over 4 is in the domain of our function or not. Then when we look at the denominator, the tangent of pi over 4 is just like the tangent of 45 degrees, which will give you 1. So tangent of pi over 4 is equal to 1. 1 minus 1 is 0. And in the numerator, we'll have 0. So we've got 0 over 0. So what we are going to do is just to rewrite this, simplify a little bit, x approach pi over 4. And remember, if you are using a calculator to evaluate the tangent of pi over 4, you must put your calculator in radian mode. Put your calculator in radian mode. Put calculator in radian mode. So I believe by now you know how to put your calculators in different modes. We have degrees, which is what you are used to. We also have radian mode and other modes which are used by engineers and so on and so on. But for our purposes, we put our calculators on radian mode. So this is what we have. Then we simplify this. We have the sine of x minus the cosine of x. We divide this. We know that the tangent of x is the sine of x divided by the cosine of x minus 1, like that. This is equal to the limit when x is approaching pi over 4. Let us copy the numerator as it is, sine of x minus cosine of x, then divide. We look now at the denominator. We are combining this fraction with minus 1. So we will speak of the lowest common multiple of the denominators. And in this case, it is going to be the cosine of x. So cosine of x into cosine of x is 1. 1 times sine x is sine x minus 1 into cosine of x is cosine of x. Cosine of x times minus 1 is cosine of x, like that. This is now equal to the limit. X is approaching pi over 4. Now let us simplify this. We have sine of x minus cosine of x over 1 multiplied by cosine of x over the sine of x minus the cosine of x, like that. So if we do that, we end up with the limit when x is approaching pi over 4. You can see this expression and this expression are the same. So they will cancel out and we're left with a cosine of x. Now pi over 4 is in the domain of cosine of x, which is going to give us 1 over 2. 1 over 2, because I don't know whether you know, let me put it here, that if you look at a right-angled triangle, let me draw it properly. If we are looking at a right-angled triangle, where this angle here is pi over 4, because this side will be 1, this side will be 1, the square root of 2. So if we speak now of cosine of pi over 4, this is just the adjacent over the hypotenuse, like that. So we end up with a cosine here of pi over 4. And when you're using your calculator, it will give you 1 over root 2, which if we want this is equal to 1 over the root of 2 times the root of 2 divided by the root of 2, which is going to give us root 2 over 2. I think this is what your calculator will give you. Okay. So we have done a number of them. You can look at those which you have not yet done and also look at what we have done and see whether you are able to do them correctly or not. So let us continue. I am not sure whether I've already discussed number 2, but with number 2, we just want to make use of the fact that the sine of theta over theta is theta approaches 0 equal to 1. And then we rewrite whatever we're given in such a way that we'll be able to apply this theorem and get the answer. So we can take, say, for argument's sake, number 1. We can take number 1. This. So 2.1, we want to make use of the fact that the limit of sine theta over theta when theta approach 1 approach 0 equal to 1. And we have here the limit of sine 7x divided by sine 5x when x is approaching 0. That's what we have. This is what we have. So how do we go about that? We just rewrite this such a way that it will be easy for us to apply that theorem. So this is going to be equal to the limit when x is approaching 0. Let me do it slowly. It is like sine of 7x over 1 times 1 over sine of 5x. All right? I haven't changed anything. So, but we want to make use of this theorem. So we may look at it this way. Instead of writing 1 here, instead of writing 1 there, we can write, say, for argument's sake, if I write 7x here, I write 5 a moment. I write 5x here. It means I have changed the setup because the original problem did not have this. So this is the same thing as having a 7 here over a 5 here. And you will notice that 7 and 7 will cancel out, 5 and 5 will cancel out, x and x will cancel out, and then we're back there. So this is going to be equal to, we know that 7 over 5 is just a constant, and then the limit of sine 7x over 7x, x is approaching 0. Let me put it this way. That's the same. Multiplied by, we're applying the limit loss here. Limit 5x over the sine of 5x when x is approaching 0. Like that. This is equal to 7 over 5 When we look at the first expression, the argument here is the same as the denominator, therefore this is equal to 1. Then here, the numerator is the same as the argument down there, therefore when we approach 0, this will be 0, that will be 0, and it satisfies this, which is 1. So the answer is 7/5. Of course, you should recall that even in the proof of this theorem, when you approach 0 like this, we can say theta over sine theta is equal to 1. So we make use of this also to evaluate our limit. Then the next one, let us see. I think 2.2 looks familiar. 2.2 looks familiar. I think we have done it maybe in the quiz. Approach 0. Just look at it. 2.2. Uh, 2.2. We have the limit when x is approaching 0 of sine squared of x over 4x squared, like that. So it's just a matter of knowing how to write this algebraically, because we have now the limit. X is approaching 0. 4 is a constant. We can write 4 like this. And then we will end up with the sine squared. Maybe I should do it slowly. This is sine squared of x over x squared. And we know that sine squared of x is sine x times sine x. So this is the same, or is equal to the limit when x is approaching 0, 1 over 4. This is sine x over x all squared, like that. So if we want to apply the limit loss to this expression that we have written, we can say this is equal to 1 over 4, the limit when x is approaching 0 of sine x over x, like this, squared. And this is 1. So we've got 1 over 4 times 1, which is 1 over 4, like that. Then, of course, you must observe how we are writing. It's important to write these things properly. Okay? We've done that one. Let us move on to, say, number 4. Let us look at number 4. We may look at number 4. Number 4 is a piecewise defined function. Number 4 is a piecewise defined function. Maybe I should write it here because I cannot copy. Number 4, what do we have? We are given a piecewise defined function t of x equal to alpha x plus 4 if x is less than 1. It will be a 4 if x is equal to 1. And it will be x squared plus 1 if x is greater than 1. So what are we supposed to do? We must find the value of alpha such that the limit of t of x when x is approaching 1 exists. So this is just, again, a concept of understanding, or we are trying to recall the concept of the limit. What do we mean when we say the two-sided limit exists? We know that the two-sided limit exists provided the right-hand limit and the left-hand limit both exist and they are equal. So that those are the things that we're going to make use of. And so if we look at, say, the limit of t of x when x is approaching 1, we can approach 1, say, when x is less than 1, it means we're approaching 1 from the left. This is equal to the limit when x is approaching 1 from the left of what? Our function now is alpha x plus a 4. That's what we have. So this is going to be equal to, since 1 is in the domain of this function, we just have alpha plus 4, like that. Let us now look at the limit of t of x when x is approaching 1 from the right. And this is going to be the limit. X is approaching 1 from the right. Then when we look at our function, we end up with the limit of this function x squared plus 1, because here x is greater than 1, so we can approach 1 from the right hand side. So we have x squared plus 1 as our tx. X squared plus 1, like this. This is equal to, we can see that 1 is in the domain of this function, so we've got 1 squared plus 1, which is 2. Now, from the existence of the limit, since the limit exists, let me write here, since the limit exists, what do we expect? We expect the limit of t of x when x is approaching 1 from the left to be equal to the limit of t of x when x is approaching 1 from the right. So we have our alpha plus 4, alpha plus 4 must be equal to 2. And you see why we are saying that you don't just claim that this is equal to that one. You must show that indeed this limit does exist and it's equal to that one exists and it's equal to that one. It's proper way of writing. So if you reach this stage, then we solve for alpha, and then we note that alpha is equal to, see here, alpha it's equal to 2 minus 4, which is minus 2, like that. All right. Then let us move on. You can look at number 3 yourself. Number 5 is about continuous functions. 5.1, we are saying find the points of discontinuity, or if any, for the function. So where do we have a discontinuity, or where does this function fail to be continuous? Then again, this is based on the definition of a continuous function, where we are saying that a function is continuous if the following conditions are satisfied. The function is continuous at a point if the following conditions are satisfied. Let me remind you. We are saying a function f of x is continuous function is continuous at a point, say A, if number 1, f of A is defined. In other words, A is in the domain of F. Number 2, limit f of x when x approach A exists. And number 3, the limit of f of x when x approach A is equal to f of A. So all these 3 conditions must be satisfied for us to conclude that a function is continuous. Now, if you check here, you will notice that we have our function. We have our function, as you can see, f of x equal to x plus 1 when x is greater or equal to 2x minus 1 when x is less equal to 2 but greater than 1, x minus 1 when x is less equal to 1. Even if we don't draw it, we can check the continuity. So we want to know the discontinuities of this function. We're saying we have a function f of x equal to x plus 1 if x is greater or equal to 2, it is 2x minus 1. If x is less equal to 2, x minus 1. If x is less equal to 1. So this is our function. So we want points of discontinuity. We want to find of this discontinuity. How do we deal with that? Then we note that we have 2 and 1. So we are checking whether our function is continuous at 2 and also at 1. So If we speak of 2, we notice that if you evaluate f of 2, was it given like this? There's something wrong with this problem. Let me check. X is greater than 1. Okay, it is this straight line, then this straight line, then that straight line. Let us look at it and see. This one here, there's something missing. That's a little bit bad, huh? So we can speak of f of 2. F of 2 in this function, we notice that f of 2 is 2, for the first part, it will be 2 plus 1, which is 3. All right. And let us check the continuity of this function. Of course, the limit also exists, because if we evaluate the limit of that portion, when x is approaching 2, either from the left or from the right, we'll have x plus, x here, x plus 1, which is 2 plus 1, which is 3. So we can see that this, hello, is equal to that. So it is continuous at 2. Now, if maybe you are going to class, just leave the meeting and go to class, whatever. I will share the recording when I finish. Just leave quietly. Don't disturb me. I'm saying if you want to leave, just leave quietly. Don't disturb. If you want to leave, just leave quietly. Don't disturb us. Okay. So where are we? Okay, I was just saying that if we check at 2 for the first function x plus 1, we see that the function is continuous. Let us look at the second branch of our function. And for the second one, we are looking at 2x minus 1. In other words, we are looking at the interval 1, open interval 1 on 1, 2. It's a half open interval. Also on the right, it's closed. On the left, it's open. So what do we have in this interval? We are saying we have 1 less than x less equal to 2. Because we know that this is the same interval as 1 to like this. So let us check whether it is continuous or not. So we will observe that we can talk of the limit of our function f of x as x approach 1 from the right. This is going to give us, we look at what we have here, 2x minus 1. So we end up with the limit x approach 1 from the right. We have 2x plus 1, which is equal to 2 plus 1, which is 3. But if we talk now of f of 1, you can see that f of 1 is not defined. In fact, 1 is not in this interval. This is a half-open interval. So f of 1 is not defined. Therefore, this function is discontinuous at 1. F of x is discontinuous at a equal to 1. That meant because f of 1 is not equal to the limit of f of x when we approach 1. So from that, we can go on and look at 2 for the second part. And of course, it is defined. Even for the third part, in the interest of time, we will notice that f of 1 will be 0. And then the limit when we approach this 1 from the left will also be 0. Therefore, it is continuous. So the point of discontinuity, or the function is not discontinuous, it's discontinuous at a equal to 1. Or in other words, it is not continuous at a equal to 1. That's the idea behind this kind of a question. Then 5.2, we are looking for the value of c such that this function is continuous at throughout. We want the value of c that we are given x less than 0, we have that. X greater or equal to 0, we have that one. So we are looking for the value of c that will make this function continuous at, say, x equal to 0. Let us look at it quickly. So they are saying find the value of c such that f of x equal to, what did we have? I think we had x cotangent of 5x if x is less than 0. We have x squared plus c if x is greater equal to 0. So we want to find the value of c such that this function f of x is continuous at x equal to 0. In other words, our a is 0. So again, we make use of our knowledge of the definition of continuity, that we may talk of the limit of our function. Just if we look at the definition, the order tells us that we can talk of f of 0. F of 0 is when x equal to 0, x is equal to 0 here. So f of 0 will just be 0 squared plus c, which is c. From there, we talk of the limit when x is approaching 0. This one is approaching 0 from the left. Our function is x cotangent of 5x, like that. So this is going to be equal to the limit when x is approaching 0 from the left of x. Cotangent is the same thing as cosine divided by sine. Let us erase this. Cotangent is cos 5x over sine 5x, like this. So this now reminds us of something that we've already looked at, which is going to be equal to the limit when x is approaching 0 from the left of x over the sine of 5x. Multiply this by the cosine of 5x, like that. Now you will observe that here we have x, down there we've got 5x. So it tells us that we can multiply here by 5 and divide by 5, like that. So this is going to give us the limit. This is going to give us the limit. X is approaching 0 from the left. We've got 1 over 5. 1 over 5. Then 5x over the sine of 5x times, again, the limit. X is approaching 0 from the right of the cosine of 5x, like that. So this is equal to 1 over 5. The limit of 5x over sine 5x when x is approaching 0 is 1. Multiply this by the cosine of 0, again, it's 1. So we end up with 1 over 5. Now, we note that f of 0 is equal to c, and our function is continuous. So we say that since f of x is continuous, the limit of f of x when x approaches 0 must be equal to f of 0. So, and we have f of 0 equal to, oh, maybe we should stop here. Hello? Hello? Hello?